In this example, we use enthalpy as a conversion factor in dimensional analysis after taking into account percent efficiency. Our problem reads, butane is used as a fuel for portable stoves. Suppose a pot of soup must absorb 955 kilojoules to fully cook, and that the soup absorbs only 18.0% of the heat released by the fuel. What mass in grams of butane is needed? Our first step is to calculate the amount of thermal energy needed to fully cook the soup, taking into account the percent efficiency. We can use our percent yield equation to do this. In this equation, the percent yield is the efficiency we're given in the problem. The actual yield is the amount of thermal energy we actually need the soup to absorb, and the theoretical yield is the amount of energy we need to produce. We can rearrange this equation to solve for theoretical yield. Then we can plug in our numbers from the problem. We want the soup to actually absorb 955 kilojoules, but only 18.0% of the thermal energy produced is actually absorbed. Completing the calculation, we need to produce 5,306 kilojoules to fully cook the soup. Now we can calculate the mass of butane needed to produce this thermal energy. The thermal energy released by the reaction is absorbed by the soup, so heat released equals negative heat absorbed. We need our reaction to release 5,306 kilojoules, and releasing energy is a negative change in heat. So we start our dimensional analysis with negative 5,306 kilojoules. We can use the enthalpy of solution and the coefficients in the balanced chemical equation to convert from kilojoules to moles of butane. 2 moles of butane will release 5,748 kilojoules according to our equation. Then we can use the molar mass of butane to convert from moles of butane to grams of butane. Completing the calculation, we get 107 grams of butane are needed to cook the soup.